Step 5, does this mathematical field calculation match what our initial intuitive assessment was? We have two critical points that we looked at. One of the critical behaviors that we were looking at is that as z gets very large, in other words, z much, much greater than r, the charged disk appears as a point charge. I will check the limit z much, much greater than r two ways. And as I've been calling it, the cheap way and the proper way, let's look at the cheap way first. So the first case that we want to look at is we want to look at the cheap way. That means you're not investing anything into it. All we're going to do here is that if z is so much bigger than r, we could effectively just set r approximately to 0. So if I look at the limit as z is much, much greater than r of the disk, what do I get? Well, I have my constant term in front, and then I'm taking this limit. So then I have this minus r squared z squared square root divided into z. And we're seeing here is that if we approximate it like that, then I'm going to get 2 epsilon naught. And then I'm going to get a term that reads 1. Then I'm going to get what? I'm going to get 0 plus z squared square root over z. And you can see right here, what am I going to get? I'm going to get 1 minus 1, which is 0. This cannot be correct. Since it gives a nonsensical answer. We already saw that the physics way claims point-like. So if it claims point, the field of the disk here should have been that it went to a point, which then says it should be E point, and it should be 4 pi epsilon r squared divided into q. That's what we should have gotten. It's not that. So this way does not work. It doesn't make any sense. It's nonsensical. So now we have to do it the proper way. So you got to pay attention here and make sure that you're following the physics. And this way, we're going to use the binomial approximation. So let's do that. So as we prepare, we need to really pay attention to the limits. So if z is much, much bigger than r, then I can define r over z which in the binomial expansion is called x, that guy will be less than 1. This means here we prepare the E-disk field equation into proper form. Okay, so the proper form then says this: I got to create that R over Z. So I'm really asking, what is the expansion parameter? And the answer is it's x equal to R divided by Z, because that's really small. So then if I take E of the disk, I'm going to get 2 epsilon. And then I'm going to get a term that reads 1 minus R squared Z squared square root into Z. So now what I have to do here is that I have to factor out that Z factor right there. So if I do that, here's what I'm seeing. If I factor it out, I'm going to get 2 epsilon eta, and then I'm going to have my term. So I have my 1. So look at that. I'm factoring out a Z. So what am I getting if I factor out a Z? I'm going to get a Z in the denominator. Then I'm going to take my square root here. And if I get my square root, I'm going to see that this is going to be 1 plus RZ squared. And then I have that Z here. And right away, you can see that this one and that one cancel out. So then if I put this into just a binomial form, I'm going to get 2 epsilon eta, and then I'm going to get 1 minus 1 plus R Z squared to the minus 1/2. So now I'm going to say that's in proper form. So now apply the expansion or the approximation. Now apply the binomial approximation. In other words, I'm now going to take the limit as R over Z is much, much smaller than 1 of E of the disk. And in this situation, I do pull out, by the way, I did not write this down, but I'm assuming that we've done this enough times, and this will then equal 1 plus nx, where all the higher order terms go to 0. Okay, so if I do that, then I'm going to write this here. I'm going to get 2 epsilon into eta. Then I get this term, which will be 1. Now look what I'm going to get. My bracket term is this, so I'm going to get 1 minus 1/2 R squared Z squared, and then I have the higher order terms that we ignore. And you can see here is that this one and that one, they sum to 0. They cancel out, which then means I can approximate this guy as 4 epsilon Z squared over eta R squared. Now we calculated the charge density earlier, and this is what we found, that it's the charge density over a circle, so it's got to be the total amount of charge, Q, times pi R squared. So if I plug that in, you could see here is that the r's cancel. I put a pi down here and I get q instead. You're going to find here is that this then gives me the result of 4 pi epsilon z squared divided into q. And right away, you can see that this agrees exactly what we expected here. So this agrees with our initial assessment of the field. Now you can see why the proper way works. The cheap way, which I use too, by the way, if it gives a nonsensical result, you got to go back and do it the proper way. Now let's look at case 2. So here, we're now going to set it up so that as, I think, how did I write this? I'm going to say, yes, okay. We're doing this as z gets very close to the surface. That really means that z here is much, much smaller than r. The finite disk now appears gigantic. It appears as an infinite plane. So the question was, is that we expect that the E field of the disk, that in the limit as Z is much, much smaller than R of the disk, we expect that to look like an infinite plane. Which we said was going to be a constant as you walked around that infinite plane surface. So let's do it two-way. Okay, let's do it two ways. So here, we're going to look at the cheap way. And here we're going to set z equal to 0. So if I look at that, or just z almost at 0, we can't set it to 0. So then once again, I really have this guy again, so I think I'm just going to steal it, right? I'm just going to copy this guy right here, because that's the exact same write-up. The only difference here is that I'm looking at the limit as z gets much, much smaller than r. And if you look at this, what am I actually seeing? Well, you could see here is z is getting very close to 0, so then I can approximate the field. So if z is equal to 0, then I'm going to get 0 over r. I'm going to get a value that reads eta divided by 2 epsilon. And look at that. That's a constant. And that is an important result. Infinite plane. And this is what we came to look for right here. Now I can do that with the binomial expansion and I'll get the exact same thing. Okay, so if I do the cheap way, the proper way, then what I'm going to do here is that I again start with the same equation here. I start with the same equation, and then we're going to say the proper way. And that tells me that z is much, much smaller than r. Well, let's see if we can do this quickly. So if I look at this, the first thing that I got to do here is that I have to factor out R, right? So I need to factor this guy out. And if I factor it out, I'm going to pull out the R. And this is what I see here. I'm going to see here that this will give me eta over 2 epsilon. Then I'm going to get a term. So if I factor out, I'm going to get z over R. And then I'm going to get 1 plus z over R to the minus 1/2. So we expect that term. So if you're looking at this, we already know what the answer is. So we're expecting this term here should go to 0. So how do we know? Well, we apply the binomial expansion. So applying the binomial approximation, we then get the following. I'm going to take my limit, right? There's my limit right here. And as I take my limit here, I'm really looking at this guy here. So if I look at a binomial expansion here, I'm really looking at z over r, which will be less than 1. So then if I look at this thing, I've taken this out. This is to the 1/2. So this is going to be 1 minus z over r. And then this will be 1 minus 1/2 z squared r squared and all the higher order terms. So when I start to look at this thing, when it cleans up here, I'm going to get that this will be eta 2 epsilon. Then I'm going to get a term that's 1. Then I'm going to get z over r plus 1/2 z squared over r squared. And I keep going on. So note that these two terms right here, these are much smaller than 1 and therefore ignored. So that gives me a result of, again, of eta over 2 epsilon naught. So now that I have agreement with both of them, we could then come in here and say this. We have agreements, on the field behavior which is that the infinite disk is then going to be eta 2 epsilon, which will be equal to a constant. That's what we came to do right here. So now what we want to do is that we want to interpret this field. So there's a lot of really great physics here. So now, interpretation of the infinite plane field. So one of the things that I find really interesting is that note that the electric field of the infinite plane is a constant. In other words, it does not contain the variable z. This is a surprising and correct equation. So as I'm saying here is that it's surprising that the infinite plane field does not contain z. This means the field produced by this infinite plane is independent of distance from the charged plate. So here are some questions that we have to answer. What do we really mean by an infinite plane in physics? You can't go to the store and buy one. You can't go and look for one because they don't exist. So they have to have some realistic definition. What happens to Coulomb's law that states fields are position dependent? In other words, we see here that our little fields are proportional to 1 over r squared. How can we have a constant field if Coulomb's law says that they have to depend on position? The way we've been talking about an infinite plane is r is much, much bigger than z, as long as the point P is located in the middle of a large plane and extremely close the plate to plane is infinite. And we talked about this before when we numerically checked the finite line versus the infinite line values. It depends on how many sig figs you're willing to deal with. So how do we achieve an infinite plate approximation in the lab? So picture-wise, one uses two finite parallel plates with the point charge or the point P in between them. Now you might ask the question, why do I need two? We don't, but it just makes it easier to see what we're talking about. So here's two parallel plates. So if I put a little point in between these two plates that are really closely separated, and mine in the middle, I actually can't see the field at all. And to show you what I mean here is that imagine that I have two plates. Okay. I have two plates. So the picture that I'm really trying to show you is that I'm saying that, yes, I have two plates like this and they're vertical, but I'm going to draw them horizontally. So I need to draw them as close as I possibly can. So I imagine two very, very, very long plates. Now, what I have to do is that I have to create the same thing, but now I got to bring these as close as I can. And you can clearly see that there's a separation right there. So if I come in here, I'm going to put my point right there. That's going to be my point P. Now what I'm seeing here is that because it's so close, I'm clearly seeing here is that I can't see the ends. It's an infinite plate. So I have a software that can actually run an infinite plate. And when you look at the infinite plate, here's what you're seeing. Here is the infinite. So right here, you're seeing that this line right here is a finite. It's not the way you spell finite. Finite disk or plane. And what you want to pay attention to here is that if I pick a point in the middle, so again, I'm going to say that I'm going to pick a point right here, really, 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 really close to the plate. And you can see that blue line represents the plate. So when I look at this thing, this is what I see here. What I see right here is that I see that about right in here, I am seeing no fringing of the field lines. And so what that tells me here is that all lines are parallel. So if I'm within that region, that's an infinite plane. But if you step out here, you're seeing here, you could see that there's an angle. And what this is called here, this is called the fringing of the field. which then tells you you can then see the ends. And if you can see the ends, then that tells you that you're dealing with a finite plane field. So we drew this before, but let's keep drawing this. So I'm looking at the middle. So if I'm looking at the middle, remember, it's a finite plane, but we can treat it as an infinite plane. So then once again, we can draw these fields as long as no fringing occurs. So if I pick a small plate, let's say that I have a plate like this, and I'm looking at this plate. And so if I start to sort of like imagine that I have my point P here in the middle, and then I have my thing, as long as these electric fields around P look uniform, then I can use the infinite plate field that we calculated. I can do the exact same thing. And so you could see here is that this is a positive infinite plane. And if I do the same thing for a negative one, instead of them coming out, poking out, these guys are going to be going in. So then I come in and I put in my fields. And as long as those fields look the same everywhere, I cannot tell that it's a finite plate. And of course, this is the negative infinite plane. Now, if we try to do a finite plane, here's what we're going to see here. So if I have a finite uh, parallel planes, and I'm going to call them plates right now. Here's what we're seeing. I have two plates, and I'm going to charge one positively. And I need to move this down. And then I'm going to do the same thing with the green plate. Oops. So what I'm saying here is there's positive, 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 positive. Then I have negative plate here. Now note that there are two fields in between. There's the field due to the positive charge, and then there's the field due to the green charge. But what I'm going to do is that I'm going to ignore those fields for right now. And so what I see here is that I see this. I see the fields being parallel right here. So as I get closer to the edges, I start to see the field fringing. So I'm starting to see the fields bending and bending more and more. And this is what we call fringing. So then if I do the exact same thing on the other side, If I was to take this guy, and I don't know how to really do this, but I could imagine that I could probably just cut this. Can I cut this? Can I just copy this piece? And I paste it. Oh, I can. And then I come and I paste this right here. And I copy this right here. Oh, man. So now look what I want to do. Here's what I'm really trying to show you here. What I was trying to do was trying to do this. You could imagine that I can literally separate the plate. I think I'm not going to do this. So if I could separate the plate, you could see that this is due to an infinite plane. And then the blue edges right here, this is due to a finite plane. You can separate out the two fields. So it's only a small region that happens. So now let's go to the second question. Coulomb's law clearly depends on position. But the infinite plane does not. The question is why? So to answer this, I want to go through a thought experiment. And it is a super cool thought experiment. So when I'm thinking about this thought experiment, we've been talking about the infinite plane. What you have to do here is that you have to stand really, really close to a large finite plane. So let's draw this plane here. So I want to look at this plane, and this is what I'm thinking here. I have an infinite plane, and so I want to copy this and paste it. So we know that we have, this is the side view of an infinite plane, and it has field lines that look like this. And I'm assuming that I'm close enough that all of the field lines are, they're all uniformly spread out as expected. So then what I'm going to do here is that I'm going to pick my point in the middle here, and I'm going to say that this is my axis right here. And that's what I'm going to put my point on. So now I need to make 3 copies of this. And I'm going to try to space them out nicely. Yeah, so here we go. So now in this thought experiment, what you want to do here is that, so you're very close to the finite plane, and start moving away. Okay, you're going to start moving away. So if I'm right here, that's my point P. Let me make this a little bit farther away. I'm going to say that this is my point right here, P. Okay, so this is my point P right here. And what happens here is that I'm going to call this number 1, number 2, and number 3. So this is situation number 1. At a point P very close to the plate, there is a small field of view that saturates your vision. So what I mean by that is that imagine now is that I look towards this thing. What determines the 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 density of the electric field lines is how much charge do you actually see. So in this case, as I move away, I have a field of view that looks like this, and I only see a little bit of charge, but that little bit of charge has fewer E field lines, but it's still constant. So what I'm saying here is that for the amount of charge that enters my view, there are fewer E field lines with constant line density. But the line density is still the same. So now what I'm going to do is that I'm going to move farther back. So let's say I'm right here at this point P. So now what I'm seeing is that my field of view has now grown. So in most cases, what actually happens? If I move away, my line density decreases. But that's not the case here. And two, what you're seeing here is that as we continue moving backwards, I see more charge, and therefore more lines of E field. It contains more charge, but I also get more E field, but the field doesn't decrease because I've increased my charge. In other words, as my field view increases the amount of charge, the larger charge creates more field lines that keeps the line density constant. It's almost like looking at how a uniform charge distribution is occurring. but now I see more field lines, but the field has not increased. Then I finally get to point P out here. So if I pick a point P out here, now what happens is that you see that as my field of view increases, there's a point where the amount of charge now stays fixed. And as it stays fixed, it means here that I'm seeing the smaller amount of charge density, excuse me. Okay, so then if I look at number 3 here, so continuing to move away, the amount of charge in the field of view decreases. I'm not getting the same number, as well as the line density too. So as a consequence, the conditions of R being much, much bigger than Z are not being met anymore. And we now have to start using E finite disk, which is then equal to 2 epsilon eta times the quantity 1 minus R squared Z squared square root into Z.